Okay, I think let's start. So, myself is also feel very sleepy. Okay, our topic is the improvement we have made to the FreeBSD for the Hyper-V and Azure support. For those of you who may not be familiar with the Hyper-V and Azure, here is the brief introduction. Hyper-V is a hypervisor-based virtualization platform. It's, of course, developed by the Microsoft. And Azure is a public cloud service, which is primarily based on the Hyper-V. So there are differences, but it's primarily based on the Hyper-V. So if your system can run smoothly on the Hyper-V, which means your system can be run smoothly in the Azure. Here is the basic architecture. This is the Hyper-V. Then it's directly talk to the hardware. Windows Server is actually acts kind of like Zstorm Link, the .0, and the FreeBSD is running as a guest, completely as a guest. The kernel just interacts with the Hyper-V, and basic infrastructure is kind of different. The Hyper-V does not emulate a full PCI bus. It uses a private bus called the VM bus. It's use different communication protocols. So here we listed the topics covered by this talk. It's a wide range of topics. First, we are going to introduce the improvement we made to the network device drivers, then the storage device drivers, and last I'm going to show you the PCI Express pass-through functionality of the Hyper-V, and some additional functionalities like volume shadow copy service, and some handy improvement like the trim support. First, let's talk a little bit about the improvement we added to the Hyper-V network device drivers. First of all, this actually is an improvement in the FreeBSD itself, not the network device drivers for the Hyper-V. So, for the virtualization the network, LRO is actually a required feature. It's mainly because, first of all, it reduced the rate of the TCP X. As you know, several data segments are aggregated together, so you only need to send one X for several data segments instead of one X for two segments as standardized by the RFC. And well, this also saves the TCP. The LRO also saves the TCP segment and acknowledgement processing time. So this is a weak point. It's mainly because the virtualized technology is very strong in the computation power. It's almost same as the bare metal. Its computation power is almost same as the bare metal. So this is a weak point. But the strong point is reduce the sending rate of the TCP ACK. Why the reduction is very important? It's mainly because sending very small packets in the virtualized environment is very it's extremely costful. So you want to reduce this small packet sending as much as possible. So this is the precondition that we try to improve the TCP LRO for the FreeBSD. And the next is we try to increase the number of LRO entries that we could use. For example, for the concurrent connection at 10 kilo connections concurrently, we will require something like 128 entries for LRO entries. So each TCP flow can get an LRO entry. So the LRO is more effective than the default setting. FreeBSD default setting for the LRO entry is just 8, which does not fit the concurrent C10K problem. So, at this step, we got a large amount of LRO entries in the LRO structure. But we noticed actually a very weird performance like a high standard deviation. We take a more close look at the LRO. What actually happened there is that all LRO entries are actually linked by a list. So if you want to find the LRO entry on the input path, it's very costful. You will have to go through the whole list, find the entry, and include the packet. let's talk about the solution. There's actually two types of the improved LROs that we can use. The first is actually currently the default method that we have deployed on the FreeBSD is the hash table. The hash table is kind of pretty obvious. It reduced the search time. So the LRO entry lookup will be very fast. To be frank, it's not completely developed by us. It's proposed by Glatton and Randall Stewart, I think. RS, his commit name is RS. We adapted that patch, cleaned it up a little bit, and committed it into the FreeBSD system. The hash, how the hash is computed, it's actually completely based on the, let's say, the RSS hash. It's provided by the hardware. And for this hash table, I will have to note the primary hash should be used instead of the power of 2 hash table. Because the RSS is trying to distribute the packet using the lower bits of the hash. So if you use the power of 2 hash table, you got a severe alias problem. It's because for ring 0, you get, if you have 8 rings, then you get the hash value like 0, 8, 16 on that ring. So if you use power of 2 hash, only very small portion of the whole hash table will be used. So here we use the primary hash, which does not have any alias problem. Here is the performance improvement for HTTP 1.0 1 kilobyte web object. As you can see, it's kind of clear here. As you can see, the green line is the hash table LRO, and the purple line is the original linked list LRO. The performance improvement is kind of noticeable, at least 10%. And let's see, these two lines may not be very clear here. It's the green line is the original latency and latency average, and the orange line is the average latency of the hash table LRO. It also gets at least noticeable reduction. And for relatively large web object, as we can see for the 16 kilobytes object, the performance improvement is much higher than the 1 kilobyte web object, and also the latency reduction. So there also exists the plan B. It's not the default. It's not the default, but you can enable it. It's developed by the APS, actually at the same time as the hash table LRO. The whole working mechanism is kind of different from the hash LRO. Driver just enqueues the received packets without searching LRO entries at all. It just enqueues, like for example, 200 packets or 500 packets into array. Once the threshold, for example, 200 or 500 has been reached, the LRO code will try to sort the whole array according to its hash. Then it will pass the packet to the standard LRO function one packet each time. But at this time, the LRO actually it is sorted. There is no searching cost. So once the different hash is detected, the whole packet is dispatched to the up layer. So it actually can achieve the same effect as the hash LRO. Sometimes even a little bit better. It's primarily based on your workload. But as I have said, you will have to tune the up limit, which means when the sorted LRO is going to flush the cached entries. It can be 200 or 500, maybe sometimes other values. You will have to test it, measured based on your workload, based on your own workload. It's not always a performance and a latency winner compared with the hash table. For example, as we can see here, for this picture, 14 requests per connection. I think it's for 1 kilobyte object. In the first picture, it's quite obvious the sort LRO is the winner. Its latency is lower and the performance is noticeably higher. But in the other situation, like 14 requests per second and 14 kilobyte object, the performance improvement of the sorted LRO is quite minor. But as you can see, the green line is the latency of the hashed table LRO, and the orange line is the sorted LRO's latency. The latency drop is, the latency increment of the sorted LRO is quite noticeable, so it actually does not worth the trouble here. So these two pictures primarily means you will have to do the test for your own workload before you enable the sorted LRO. So the LRO is good, but depends on your use case and depends on your settings. So you will have to test and various settings like the threshold for your own workload, and maybe you can just use the hash LRO, which is pretty good for almost all cases. So for the FreeBSD, we currently just use the hash LRO by default. But for the Hyper-V driver, we have a special tunable for you to enable the sorted LRO, and it allows you to set the threshold. But as you notice, it's tunable. You cannot change it at runtime. So for each of your tests, you have to reboot your virtual machines. But I think that's not a problem for virtual machines. So the next improvement is the multi-packet RDNS message. It's this looks pretty weird. First of all, it's for the non-TSO transmission. Well, we have TSO for so many years. Why do we try to improve non-TSO cases? First of all, there are many cases actually TSO cannot be used. For example, DNS is obviously not TCP, so no TSO at all. And packet forwarding, of course, you got no TSO at all. And bridging, same case as the forwarding. And the TSO also have a very ugly bursty issues. You got very long burst for a single connection. And of course, that will cause a lot of fairness issues. For example, modern NICs have multiple transmission queues, and the transmission queues are actually scheduled in a round-robin fashion. If you use TSO, then it's actually round-robin on the TSO packet. So you got a very bad fairness issues. One TCP stream is going to send something like 40 kilobytes data. Then another stream is going to send 16 kilobytes data. It's pretty ugly. And another case is like active queue management and packet scheduler. Like Colo, these days, it's actually not very TSO friendly. And the last point is actually many FreeBSD vendors and consumers don't use TSO at all, probably due to the issues I have listed above. And what's the weird multi-packet RDNS message? It's kind of like TSO, but it can aggregate completely unrelated packets together. It can be IPv4 packet, IPv6 packet, and the content of the packet can be a UDP packet or a TCP segment. They do not even need to be sent to a single location. So you just get the packet from the queue. If you can aggregate, you just put them together and send to the Hyper-V in one shoot. This greatly reduces the cost of sending small packets, because we can at least aggregate something like 8 packets for very small segments. For example, the TCP acknowledgement, we can aggregate at least 8 TCP acknowledgements into one RDNS message and send to the hypervisor. This reduces the cross-boundary cost, for example, which may cause VMX sites. It's great impact to the performance. Yes?
So when you bulk up 8 ACKs, does it have a negative effect on the timing machinery in TCP? Do you get bouncy TCP performance?
No. We don't get bouncy TCP performance in this case. The aggregation is not like it does not work like we have to wait 8 packets. It's just maybe you just have one TCP ACK to be sent and no other packets. Then we just send that packet out. It's kind of like the hardware's aggregated the doorbell write. Okay. For example, you aggregate several packets and just write to the doorbell registers. But I think this version is kind of enhanced TSO, much better than TSO in its utilization. And the performance improvement for the non-TSO cases is pretty large. It's like more than 30%. And the latency reduction, as you can see, it's amazing. Yeah, I can use that word. Next improvement we have introduced is the per-channel polling. First, we are going to give some brief introduction of the channel. On Hyper-V, a channel consists one ARX buffering, reception buffering, and one transmission buffering. Transmission buffering is only used to send packets. It's kind of like a hardware's transmission ring. But unlike the hardware transmission ring, it does not receive the send-done event. It's just used to do the sending. And there is the receiving buffer. Receiving buffer is used for two purposes. One is to receive network packets. You got packets from the network. It comes into the receiver ring. Another purpose it serves is going to receive the packet send-done event. It's kind of like a loop back. You send packets on the send buffer, and you get send-done on the receive buffer. So in this case, the receive buffer is actually the only source of the interrupt. So as long as we disable the receive buffer's interrupt, then we don't got interrupt at all. It's showing in this picture how the polling is done. This picture is the interrupt cases. We got interrupt in the VM bus interrupt network ISR, and we try to disable the interrupt in the ISR directly. It's run in the interrupt context. Then we schedule the task to per CPU VM bus task queue, and in that thread we try to process all the received packets or handle the send done, and then we flip it back to enable the interrupt, all marked in by the red. So this is the interrupt cases. But why do we need polling here? First of all, Hyper-V's network device lack proper interrupt moderation mechanism like most modern network NIC supports. Like you can throttle the whole interrupt rate. Under very high packet rate, we have observed like 8,000 ticks per second on each CPU, and 1,000 ticks in timer interrupts on each CPU under the real heavy network load. Next is why FreeBSD's on polling is not suitable here, as well, FreeBSD on polling is actually an NIC based, so it's not actually suitable for the network device driver which supports multiple transmission and multiple reception rings. So we got some homemade per-channel polling here. This illustrates how these things work. We always disable the interrupt on the ARX buffer. It is marked by using green color. We always leave it disabled, and we utilize our per CPU callout and run the callout at the cdirect exec, so we save some callout thread scheduling cost. And for this to run, we will have to enable a tunable, its current pin PCPU SWI. The callout itself will happen on the CPU that we have intended. For this case, the CPU X. The CPU X owns the channel Y, so the timer interrupt only happens on CPU X instead of on some other CPUs, and which will require the IPI to schedule the task queue. Okay, next is the performance improvement. There are minor performance improvements for the polling on FreeBSD. But the latency reduction is quite noticeable. It's like more than 30% in this case. So next we are going to talk about the improvement for the storage device drivers. First of all, it's the almighty Unmapped I. The Unmapped I was implemented by KIP, I think, in 2013 also. Yeah. It's mainly used to avoid the TRV shootdown. So avoid the TRV shootdown means you avoid all unnecessary cross-CPU IPIs. Well, on the virtual machines, cross-CPU IPIs equal to the VMX site. The VMX site actually impacts the performance most. So if you avoid the VMX site, you improve the virtual machine's performance itself. But how to utilize the Unmapped I/O? It's actually pretty simple in FreeBSD. We just switch to busdma APIs and then turn on the PI unmapped in the driver. But here comes the ugly case. Ugly case. It's actually pretty ugly for NVMe and actually exists in Hyper-V. I think NVMe 1.0 is kind of maybe involved. Microsoft, I think, yeah, it's probably the case. So NVMe 1.0 shares the same design. It's called the physical region page list. It's kind of a weird thing. The requirement is, except for the first page and the last page, all pages in the middle of the buffer need to be a full page. The first page can have non-zero offset, but it will have to consume the whole page, consume the rest of the page, and the last page will have to start from offset 0 and consume some space there. So what's the difference between a physical region page and a normal scattered list? The difference is shown in this picture. A normal scattered list is shown on the right. It can be in some random places. The buffer content can be in some random position in the whole list. But for the physical region page, you will have to be exact this way. Anything else is not a physical region page. This actually caused some trouble for the busdma API, which does not actually support the physical region page at all. So currently, the Hyper-V storage device driver only supported CAM data BIO, which actually contains the data conforms to the physical region page list, and the CAM data VADDR also conforms to the physical region page list. But we have deep trouble with the CAM data SGP ADDR or the CAM data SG CBBs, CCB at least. They are not very well supported. We have kind of like some broken hacks for the CAM data segment, but I really don't know whether it actually works or not. But as long as the buffer list is conformed to the physical region page, it can work. So next is the performance impact. Well, Unmapped I is obviously a winner here. As you can see, you almost cannot see the original performance in this picture. It's in the purple. I can see it. You probably didn't see the performance there. So next is the new channel selection algorithm we deployed to the Hyper-V storage devices. Hyper-V storage devices have multiple channels. The channel it's almost similar channel concept that I have explained for the network device. But the storage devices channel is kind of, you can compare it with the NVMe submission channel and completion channel. Then the channel selection is kind of similar to the NVMe submission channel selection too. So what's wrong with the old algorithm? Why we need the new algorithm? Old algorithm is kind of acting in a very weird way. For example, on an 8 vCPU FreeBSD Hyper-V virtual machine, we will only have 2 channels per storage devices. And in this case, the old channel assumes that the closest heuristic. For example, if the channel 0 is bound to CPU 0 and the channel 1 is bound to CPU 1, then CPU 1 to CPU 7 is actually close to CPU 1. So the channel 1 is used for all of the traffics that's generated from CPU 1 to CPU 7. So that caused a serious issue. Channel 0 is actually underutilized, but channel 1 is kind of abused here. So we actually we invented a new algorithm. It's pretty simple. We just use the current CPU and the LUN ID as the entropy, and then modulo the channel count. Why we added LUN ID here? Because it's primarily for the Azure. Because in the Azure, in order to maximize the performance, you will have to add multiple disks into your virtual machine and create a RAID 0 volume through the geom. So LUN ID is very useful as an entropy in this case. Again, the performance improvement and latency reduction. We also get great performance improvement for the new algorithm, and latency reduction is also great, more than 60%. So there are actually many interesting observations for the storage devices, because for storage devices the latency is actually much easier to measure than what we can do on the network devices. So the interesting discovery is that if you send a command on a hot channel, which actually currently is executing a command, the latency will be half of the latency. Command latency if you send a command on a completely empty channel. So There are some future works that we can explore in the upcoming developing cycles to try to do more better channel selection. But currently, one is also working pretty good. Okay, next here we see we conducted some case on using the NVMe devices on the bare metal, and we used the NVMe disk as the virtualized disk. The thing we have noticed is, well, the FreeBSD bare metal performance for the NVMe device may be actually lower than we use the virtualized disk. As you can see, the purple bar is the FreeBSD bare metal performance for the sequential read and the sequential write. The green bar is the performance of the FreeBSD VM. We use the same NVMe disk as the backend, and the blue line is the Windows performance. It's actually bare metal. So I think FreeBSD's NVMe driver may suffer some issues here. It's quite strange. Its performance is so low. But well, it's an identification here that FreeBSD on Hyper-V using NVMe as the backend for the disk emulation have higher performance. Okay, next we are going to talk about the Hyper-V PCI pass-through. Hyper-V's PCI pass-through is kind of different from other hypervisors, I think. Here it does not implement a full-featured PCI Express bus. It will require a driver on the FreeBSD side, but the driver is actually kind of simple. We only need to override the 3 PCI bus DB methods to get it done. So it's not that difficult. What's the benefit? I think primarily the benefit is on the Hyper-V side. So they can implement the PCI Express bus emulation in a much less error-prone way. For example, the MSIX. If you want to track in the MSIX application on the hypervisor side, it's kind of difficult, or at least to me, it's kind of error-prone sometimes. Here we show the big picture of the PCI pass-through for the hypervisor. As you can see, the VM bus is actually the parent of the pass-through the PCI bus. The pink one is the pass-through the PCI bus, and with one of the NVMe controller and 140 gigabits NIC. The whole bus comes with the device, and once you stop the pass-through, the whole bus also goes away. It will not. The bus itself will not linger in there. There are some memory allocation issues. For a device on the physical machine, the device's memory bar is normally allocated by the BIOS. But in the hypervisor cases, the Hyper-V, the driver of our PCI bus will have to allocate the memory. How to allocate the memory? The memory itself is a group of resources that reside on the ACPI or on the traditional PCI bus. The traditional PCI bus only contains something like older ATA emulation, but it contains all of the memory mapped I/O spaces. We then link all of the it's come from I think the CRS object of the ACPI device. Then we link all the resources together on the VM bus. So its child, for example, PCI Bridge 1 and PCI Bridge 2, can find the resources and use that resources to fill the device's VAR. In this example, this yellow VAR is allocated from VM bus's yellow region, and the green VAR of the 40 gigabit Ethernet is allocated from the green region, as shown in this picture. And its configuration, the PCI configuration space accessing is also a little bit special here. Normally, you just access a memory mapped I/O region. It's allocated, I think, by the PCI Bridge 0 normally. In that case, you share the whole configuration space. But For the PCI pass-through in the Hyper-V, it's kind of different. Each PCI bridge, each emulated PCI bridge will require a configuration space. Also, the configuration space is allocated from the resource list. As you can see, the red one, the red pair, and the blue pair. Next is MSIX and the MSIX data and address translation. It will require us to explicitly translate. For example, normally the MSIX data and address is actually allocated by the Nexus device drivers and then passed all the way to the PCI bridge. In this example, the PCI B2 is going to allocate the MSIX data and address. The Nexus 0 allocates the data and address and pass it to ACPI 0 and to the VN bus 0 and then to the PCI B2. In PCI B2, we do a special, special communication with the Hyper-V. Then the Hyper-V will tell us the translated MSI data and address. It's actually in some remappable format. You can find that format on the Intel document. Then we write this remappable MSIX data and address to the MSI registers. So that's all we have done for the three methods. Next, what brings us? Of course, it's the performance improvement. The PCI pass-through gives very high performance. For example, for the TCP bulk data transmission, it gives almost a line rate for 40 gigabit Ethernet. But if we use the same physical Ethernet as the virtualized backend, then we only get 25 gigabits per second. And the pass-through is actually the stepstone for the SILV support in the Hyper-V network device. And for FreeBSD, current, we actually have committed that code, the SILV support. And I also think we have backported it to FreeBSD 10 and FreeBSD 11 stable. Next is the volume shadow copy. It's I think you might know the snapshot of the virtual machine. It takes you just click a button and the whole virtual machine is got snapshots. It saves the register memory and disk and maybe many other states. But Hyper-V's volume shadow copy service is only going to save the content on the disk. So as you can see, it will have to ask the operating system and user land application to cooperate because you will have to flush any pending buffers there. So the whole thing is kind of work like this. There's a lot of massive communication. For example, once you have clicked the button to do the shadow volume copy service, then Hyper-V will ask the kernel, I'm going to start. Then the kernel will send all the message to the user land. For example, if you have the UFS mounted, then a default user land daemon will try to say, okay, we are going to do the ZSS. Fine. If you only have the UFS, then that's okay, but ZFS is not currently supported. Then it's going to check the user land daemon. The user land daemon is normally developed by the users. We don't have the control there, but it can also missing as I have put it in a dotted square. Once this check is done, the hypervisor is going the userland daemon. The userland daemon is going to flush its own data. For example, if you database application, you then flush all of your cache data onto the disk. After that, the VSS daemon, the default daemon, is going to do UFS suspend syscontrol. At that point, all of the rights to the UFS system will be held. Once this is done, kernel is going to tell the Hyper-V, it's okay, you can take a snapshot of the disk. Once the snapshot is taken, the Hyper-V will tell us that everything is done, then you can storm and you can move on. Okay, the last is some handy features. First is the trim on the virtual disk. Why trim is important? Because it affects how much you are going to pay in the Azure. Because in Azure is only charged based on the user space. So if you don't trim, but the data you don't use, Azure will think, well, you use that space, so you need to pay for it. And the next improvement is the timer synchronization. It's kind of like NTP service, but we have improved its accuracy to take account the round trip time. For example, the round trip time starts from the Hyper-V to the FreeBSD VM. Next is the reference TSC. It's a very cheap RDTSC. This kind of RDTSC will not going to cause any VMX site. It's just running the virtual machine. So you don't have a performance penalty like other RDTSC implementation, which normally will cause a VMX site. And the last is the dynamic network access key and indirect table adjustment. It's kind of like pretty useful for some vendors if they want to change the indirect table to do some load balance. So what's going on? The first point is actually committed. We have committed the code for the SRLV support. Currently, it works with the Mellanox Connect X3 card. This has been in the FreeBSD current and 10 stable and 11 stable. Next is the Hyper-V Generation 2 VM bootstrapping. It's mainly the UEFI. I think the patch is committed to the current. And let's see, the synthetic keyboard. Once the Hyper-V Generation 2 machine is used, then the synthetic keyboard is actually the only keyboard that's available. But well, if you are using the Chrome console, like a normal kernel developer will use, then I think you are fine. So, any questions? No? Okay. You mean the network benchmark and the storage?
Yeah, how do you
Storage benchmark is we're using the FRO running on the raw disk. So I'm not quite sure whether running on the raw disk you are interested in running on the raw disk or running on the file system, because file system has its own impact. Yeah.
And what I want to ask is, what the software or how do you measure those improvements?
Okay, for the storage device, we just use the FRO. FRO running on the raw disk, so we test the driver directly. For the network, we use two matrices. One is not shown here. It's for the bulk data, TCP bulk data, but at high concurrency, because we don't think low concurrency is the use case. For example, we normally start from at least 500 concurrent connections and then move up to C10K. Okay. The next is the bulk data is one direction. It's only one direction traffic, right? Then the other case that we actually care, and we mostly care about, is actually the HTTP performance, 1.1. As you know, the HTTP is actually quite dominant these days. So, and it also reflects it can also effectively measure the latency improvement, because it's a request to response cases, right? And for our cases, on the FreeBSD, we normally measure the 4 requests per connection. You know the reason. Yeah. And object size, we test various object sizes, starts from 1K and 8K, 16K, 24K, 32K, and 14K. Well, only goes to 40K. But not go up. It's mainly because the average web object size for non-video streaming data stays at 24K. Okay. So it's average size. I think the statistic is based on Google's measurement, average object size. But it grows. Average object size grows, so that's why we go to 40. That's why it goes to 40. But for video stream, it's you may measure 1 megabytes. Yeah. And for the measurement, I'm using the WRK. I think you are at my talk yesterday? No? Okay, the WRK, I can send you the URL. We modified the WRK. I actually make it kind of BSD-centric to avoid several syscall overrides. For example, if you close a socket, you actually do not need to move it from the KQ first. You just close it. It will remove it from the KQ automatically. And something like socket. For non-blocking socket, we can just use the new socket API. in one socket call. Just use a socket call to make it non-blocking instead of socket then FIO. And there are some other minor things, but it's kind of useful for FreeBSD and for other BSDs. Yeah. I can send you the WRK commands that we're using, and the UIR the modified WRK workload. And we actually have a daily performance measurement. It's automatic. It's automated by one of my colleagues. It's Hong Jiang. He arrived here last time. He did the whole thing automated. We monitor the performance actually every day. He will generate a report in the morning, and we can take a look at the report. So we know whether our code breaks the performance or anything else breaks the performance. It's quite timely. Because it's daily, so you can track the commits pretty easily. Yeah, you can bisect, find the problem commits, and try to understand what's happening.
So what does that run on?
It's running on. It's the system that you are using, I think. It's what's the name? Jenkins. Yeah, it's triggered by Jenkins, and generates some reports. And Hongjiang have some tools to generate graphics, so you can have a visual view of the performance difference. And he actually saved the data of the previous day, so he can do a comparison. Today's comparison and yesterday's comparison. If the deviation, I think his set threshold is 10%, deviation is above the 10%, he sets some color on it. If it's 10% drop, it's red. 10% improvement, it's green. Otherwise, it's white. Yeah, it's visualize the tools. You should have that. Yeah, I can bridge it together, so we can share some work in this area. Any questions? Okay, I'll take that as notes.